That is called counting all. But this is still a form of counting. This is not computing. And so, unfortunately, many of our children in grade 1 are at this point right now in this time of the year. And this has not set them up for success in grade 2 and grade 3 because it still remains a form of counting. They've only met 8 as a count and 7 as a count, and they see 15 as the collection of 8 and 7. But they haven't learned any mathematical reasoning principles inside of this. This remains counting. So this is what computing looks like even in grade 1. And this is what I believe we need to be striving for. A child should be able to quite naturally break up 7 into 5 and 2, take the 2 from the 7, put it onto the 8 to get 10, and then take the 5 onto the 10 and get 15, as you saw me do over here. Another child might do it differently. Another child might say, well, I'm going to break up 8 because I know 8 is 5 and 3, and I know 7 is 5 and 2. The 2 5s together make 10, the 3 and the 2 together make 5, and the 10 and the 5 make 15. What you see happening here is you see a decomposition of numbers, which happens throughout mathematics. They need to work with that. You see a rearranging, putting the ones that are the same together, and then you see a recomposition. The 10 and the 5 becomes 15. So this all involves mathematical reasoning. I'm not talking about a particular method here. I'm talking about a thinking process that is happening. So, sorry, I just want to get to my screen that I can see. Computing in maths is not about a particular method. I'm not talking about horizontal method or vertical method. And often people ask me, which one is better? Those are methods. Those are not ways of thinking. Those are ways of writing down and communicating what has happened in our head. The thinking needs to be the understanding of breaking up, reorganizing, putting partial sums together and recomposing. And that's what computing is. It's mathematical reasoning. It's learning to manipulate numbers and figures so that later you can manipulate fractions and algebraic variables. And the mathematical reasoning is what takes you through that. And that's why these researchers are speaking so emphatically about computing being the thing that helps children to progress, not counting. So this is what composing also looks like. For example, when you are doing 18 plus 17, a lot of our learners now might be able to do this. Some of them will still count. I still see a lot of stripes being drawn, but this is what computing could look like over 18 plus 17. You could break the 8 up into 5 and 3, and you could break the 7 of the 17 into 5 and 2. It's not necessary to break the 10s up because 10 has now become our base. You would then, for example, put those 2 5s together, which is a natural combination, and the 3 and the 2, the units together, and you can clearly see that the answer is 35. We've now manipulated and efficiently worked with our numbers to get to the answer. We haven't counted on, we haven't counted all. We have computed. Another way to do it might be to only break up the 7 into 5 and 2. The 2 naturally groups with the 8 to become another 10. And there again, we've got the 3 10s and the 5, which makes up the 35. Now, again, some teachers say to me, we teach our children to go to the nearest 10. Be careful of that, again, being a method. It's come from you to the child as a teacher. It hasn't necessarily come out of the child's understanding that 10 is 8 and 2. Or if I'm sitting with a 2 and an 8, I may as well just form a 10. And this is the difference. We want the learners to be able to compose numbers naturally so that they can manipulate them to come up with these strategies, not us forcing them to do going to the nearest 10 or whatever we call these different strategies. And then what does it look like written out? This is the way of writing it. It might look like this. We reorganize the 10s to be together and the units to be together. The 2 from the 7 comes to the 8 to make it a 10, and we have a 5 left over. Another way is some people might say 10 and 10 is 20, 8 and 7 is 15. The 15 again can be decomposed into 10 and 5, and that again becomes 35. Again, that is a form of computing. The computing, though, is what's happening in the child's head, not necessarily only in the written word. Even this is another possible way of computing. The 8 and the 7 is 15. The 10 and the 10 is 20. Notice I've written it in a different way. I haven't written it horizontally now. I've written it in a column method But this isn't a method, it's the way that I'm writing it. Just written it in a different style. The 15 again becomes 10 and 5, and then my 20 and my 10 makes 30. Even this, I'm not mad about this kind of approach or this kind of way of writing it, but it still is computing because you're still understanding that 10 and 10 is 20, 8 and 7 is 15, 15 is 10 and 5, then regrouping 20 and 35. Now, this one for me is not computing. The column, I've heard this called the column method and everything. I hope you can see the difference between this one and the one I did now. Now I showed 10 and 8 and 10 and 7. Now I'm only working with the digits in this one. I'm not working with the actual value. So if I say 8 and 7 is 15, and I hear this often, 8 plus 7 is 15, carry 1. And then they say 1 and 1 and 1 is 3. So we end up having something like that, and we end up having 3, 5. But the learner has not computed with an understanding of 35 necessarily. And that's why I prefer the 18 to be written in foundation phase as 10 and 8, so that the learner is working with the tens as tens and the digits, the units as units, and not only working with the digits. Because this kind of column arithmetic, it's fine for the intermediate phase, but in the foundation phase, it's actually a form of counting. I count the one column, I count the other column. And that's literally what the kids end up doing. They end up counting in columns rather than understanding the composition of the numbers that they're working with. So this is not computing. It doesn't encourage decomposition. It doesn't encourage rearrangement or manipulation, and it doesn't encourage any mathematical reason. It just is an efficient way of counting in columns. This one too, you'll notice this one is different to the other one. Again, I haven't written the 18 out as 10 and 8. I really dislike this one. I see so many children go wrong on this. They say 1 and 1 is 2, and then they say 8 and 7 is 15. And then often they'll put that together and the answer will be 215, for example. And this is often an illustration of they're following a method and there's not an understanding of the composition of the numbers.
Where is your sound?
So for me, it's very important. It's very hard for children who have only learned about counting to move to computing. We think they make a natural move, but they actually move from counting to the methods we teach them. And so if they haven't met numbers as composites or understood that 5 and 3 is the same as 8 and 6 and 2 is the same as 8, I'm not talking about bonds. We teach them 8, and then later we teach them the bonds. We teach them 6 plus 2 is 8. And I've also heard that joke about that little kid that came home from school and she said, Mom, yesterday they told me that 5 is 4 and 1. Today they told me that 5 is 3 and 2. I wish they'd make up their minds, because I'm not going back there till they make up their minds. And so there's this kind of thinking. The child has met 5 as 5, and suddenly the teacher's saying it's 4 and 1, and then the teacher's saying it's 3 and 2. But we start the other way around. We start with 1 and 4 being called 5, and 3 and 2 being called 5. The same as when you're wearing something long sleeve that's knitted from wool, it's called a jersey, even though it doesn't always look the same. So this is the principle that we are working from or trying to encourage for composition. On the screen, you can see a child in grade 5 who has not mastered composition in any way. They are stuck counting, and this is unfortunately what we are seeing so much of. If you have a look at all the little drawings, in fact, if you have a look at 8, the child got an answer of 30. They literally added 8 and 7 is 15, 7 and 8 is 15, and 15 and 15 is 30. And this is because the child is limited to what they can count. They have no understanding of the composition of 87 as 80 and 7. They understand 87 as 8 and 7, and the column method is often causing this as well. So another one that I can show you is a different child. You can see the counting implications here as well. The child's trying to make sense of it using ones, using digits again. And then again, this one, which should be a very easy one to answer, but just because the order was different, again, the 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. The child is grappling with counts and has not moved beyond that. This is a grade 3 learner. Again, a lot of counting happening and no composition. 7 plus 30, they're getting the answer of 37, but you'll see what happens with 107. And we're not sure if they were drawing the dots to appease the teacher, because she said when you're not sure, you should draw dots. It could be. But there also seems to be a lack of engaging with actual understanding of the values of the numbers. So again, learners who are accustomed and conditioned to counting will probably do addition using counting. And we as teachers often encourage it. At least they're getting the right answer. The problem is they're not learning any mathematical reasoning, and they're not moving to computing. To try and change this, we have introduced, I developed some cards. It's not the only tool. We have a number of tools, but the easiest and accessible and affordable tool we have for schools at the moment is a pack of cards called Quanti cards. And we use these to try and encourage children, specifically when we work with the cards, to not count, but to use composition. So we prefer to do it from 3 years old when we start teaching the number system already. But even for children who are in grade 1, 2, or 3, they can switch to the cards. And then when they've got a habit of counting, we tell them, when we work with the cards, we don't count. We're going to do composition. And let me tell you what composition is. So that's what I want to talk to you about now, is about this composition. The cards look like this. There's an animal on the one side, and there are 5 different animals. This particular series is the Big 5 series. And on the other side, we have different objects. We have the object face, which has got a quantity of objects on it, and we have the animal face. So that's a 10 apple card, for example, and a lion card. For our young children, ages 2 to 4, we have the Quanti C cards, and they, for a very specific reason, only go up to 5, because we only want children of 4 years old to be naming up to 5. We show them 6, but we talk about 5 and 1, 5 and 2, 5 and 3, rather than naming 6, 7, 8, 9, 10 too quickly, because we want to force them into those compositions, and this is what allows them to do that. We also then have the Quanti-Sense range, which we often encourage grade R and grade 1. Even grade R can use the Quanti-C range, but the Quanti-Sense range goes up to 10. And then we have the Quanti-Play range, which goes up to 12, so that they start to deal with the unit of 10. But it also mimics a normal pack of cards. And so there are 13 cards of each object and 2 jokers, and that allows one to also just play fun, any card game, any normal card game that you'd want to play, you could play with that. So let's talk about how we use the cards. Now, in the foundation phase, the main question that we ask foundation phase learners is how many. In fact, I've been going through a whole lot of baseline assessments we did with learners now, and we asked them to draw, for example, if we had drawn 5 lines, we didn't tell them draw 5 lines. We just said, copy exactly what we've done. And most of the grade R learners drew lines. Or they even drew the right colored lines, but they didn't pay attention to the quantity. Grade 1, they started paying more attention to the quantity. So quantity is an aspect, the same as shape, color, object identification. And it should be an aspect that kids notice, but they only seem to notice it because they've attached it to the question of how many. And we'd love them to be noticing it even when we're not saying how many. And so the question how many typically defaults them to counting. And to avoid this, we have 2 questions that we rather ask them. And the one question is, what do you see? And now I'm quickly going to ask you what you see. I don't know if anybody in the chat wants to tell me what you see. Doesn't matter if you don't know the name of it. Just tell me what you see. I'm not sure what the responses were, but maybe you said you saw an animal with horns, which would be correct, or a dog, might look like a dog. Some people have said it looks like 4 zebra legs.
Somebody said an okapi.
Ah, very good. That's what it's called. But if everybody else didn't know that that was the name, okapi would mean very little. But well done, you're quite right. So what I'm doing here on the left side is I am describing the animal in terms of what I do know, even if I don't know the name. The person who wrote a copy was quite right, because that is the name of the animal. But I see the difference here between the description. I can still describe without knowing the name, and the name is what it is called. And I want us to apply this principle to quantities as well. We think we have to tell the learners the names of all the quantities up to 10 for them to work with those quantities. And I don't believe that's correct. I believe we can even name up to 5, and they can then work with quantities up to 25 without knowing the name 25. So let's look at that. So asking, what do you see, encourages learners to first describe something they don't know the name of in terms of what they do know. And so naming is a function of the teacher. We can name something, but we should still encourage them to describe what they see. And this is the foundation of problem solving. If you have a problem you don't know how to solve, the idea is always to go with what do I know and what information do I have in order to solve what I don't know. And that's what description encourages. Describe what you do know about this animal, even if you don't know its name. The name can come later. If we name something too quickly for learners without getting them to notice and describe the details of it, we create a culture of learning as naming. In other words, you know it if you know the name, and that's not really the truth. And similarly, if we keep working with numbers as counts and not as composites, then we create a culture of counting rather than computing. It's the composition that gives the learners the basis for computing, not the counting. So here's an example. If I ask the question, what do you see here? Some learners might say, I see apples. That's great. Some may see, I see an apple card with 2 apples and another card with 7 apples. Some may say, I see 2 cards. Some might say, I see 3 rows of apples. All of these are correct. 3 rows of 3 apples, 3 columns of 3 apples, 3 and 3 and 3, 3 threes. All of that's correct. I see red apples. I see red apples with brown stems. All of that is a description. And when we ask, what do you see in the beginning, we let them describe color, shape, I see circles, all of that. But later on, we direct them towards quantities. Specifically in terms of quantity, we see 3 and 3 and 3. For example, if I were to ask, what is it called or how many, the only answer here would be 9. And so you can see the vast openness of asking, what do you see, compared to asking, how many, because the only answer is 9.
All right, microphone, and everything over the wire in the
Competition encourages learners to be able to explain larger quantities that they don't know the name of using quantities they do know. For example, if a learner did not know the name of 10, but they saw 5 and 5, they could talk about 5 and 5. They don't know it's called 10. They can talk about 5 and 5. And this is really what we want to encourage. If a learner only knows 1, technically, if they see 3, they might not name it as 3, but they could still tell you they see 1 and 1 and 1. And that would be correct. They use what they do know to describe what they don't know. And this is the underpinning skill of computing and reasoning we are trying to impart here. It allows them to get exposed to partitioning and combining, which is a part of the curriculum, as stated in the beginning. Counting, however, only focuses on naming. 1, 2, 3. It focuses on the ordering, and it focuses on the name 1, the name 2, the name 3. And the learners don't always even get an idea of the magnitude or the value of the quantities. So this is, if you do want to look at a much longer and in-depth version of how we teach numbers as composites from a young age, you're welcome to go to the Young Game Changers YouTube channel, and there are videos on there that explain it in short 5-minute videos. But essentially what we do is we start with the smallest number, which is the smallest unit, which is 1. And then show them 2, for example, and ask them, what do you see? And if they only know 1, they would explain 1 and 1. And even grade 2s, grade 1s, 2, and 3s, when you're starting with the cards, it's good to get them to see this, to see that 2 is also 1 and 1. I'm not saying 1 plus 1 is 2, because I don't want to go back to counting or how many. I'm talking about a fact here that 1 and 1 can be called 2. In other words, if I show a 1 apple and a 1 apple card, find me one card that looks the same as these 2, and that card is called 2. It has its own name. Then we move on to, what do you see? 1 and 1. That's the description of it. That's what I see. The name is 2 cards, so they become comfortable with that. From there, we go on to 3, for example. Now they know 1 and they know 2, so I can show them that. And they can describe that to me as 2 and 1, or 1 and 2. Some might describe it as 1 and 1 and 1. No problem. That would be the description, 2 and 1 or 1 and 2. The name of this particular collection, 2 and 1 or 1 and 2 or 1 and 1 and 1, the name is 3. So you can see that they're learning to describe and name at the same time. And again, I'm talking here about younger kids. I'm not talking about addition or anything like that, or symbols at the moment. I'm just talking about the names and the descriptions. And yeah, it's very good to swap it again. 3, I show them the 3 card and I ask them, what do you see? And you can clearly see the 2 sticks grouped and the 1 stick. And the cards have been designed in a very specific way to give learners different visual experiences of the groupings and how they can describe the cards. So the 2 and the 1 combined is called a 3 card. Now you can have a look, and you can, it's not a very easy forum to interact on. I prefer workshops because then I can ask, what do you see? And I can't really do that, yeah? But if I ask you, what do you see? You can see 2 and 2 and 1. Or some people might say, I see 2 and 3. So 2 and 2 and 1, because the groups are naturally like that, or 2 groups of 2 and 1, or 4 and 1 even. And what it's called is it's called 5. 5 is the name. In other words, if I were to find one card to replace those cards, it would be a 5 card. So learners here become efficient, and it's something that they need to practice and practice, even grade 1, 2, and 3. If they're starting out with the cards, I let them practice. I show them this. I say, what do you see? 2 and 1, 1 and 2. What is it called? 3. It must actually become an automaticity. It's a bit like how we used to learn tables off by heart. I'm unashamedly saying they should immediately, when they see a 3 card, be able to break it up in their minds to 2 and 1, and it's called 3. And this helps them later for the bigger numbers. So then we start with these as well. When I see 2 and 2, I see 2 and 2. It's literally what I see, but I know the name is 4. If I see 4, I also know that it can be called 2 and 2. So there's a two-way street here. In South Africa, we often work with 2 plus 2 is 4, 2 plus 3 is 5. So the equal sign means that I must get an answer afterwards. But we also want them to learn that if I start with 4, it can be broken up into 2 and 2, because that helps them later that 35 is 30 and 5. So it needs to be both ways. And this is quite an important mathematical principle about the equal sign as well, which I won't go into today. Also, when I see 1, and so when I see 2 and 2, I know the name is 4. It's like when I see that soft serve machine, I know ice cream is going to come out of there, hopefully. Or if when I see a Steers, I know mom's going to buy me an ice cream. It's that kind of thing. I see 1 and 3, I call it 4. I see 2 and 2, I call it 4. And they can very visually see with the cards that it ends up being the same. They just change the structure a little bit, and they can see that it's the same quantity. 2 and 2, 3 and 1 can all be rearranged to give you a quantity in 4. So learners start to group objects with their eyes, initially in smaller quantities like 2s and 3s, the grade 1s, but later on they should start to see, the grade Rs, later on they should start to see groups of 5 and groups of 10. I don't know how many of you are using synthetic phonetics in your teaching. I know in the Western Cape they've rolled out with that in the literacy. And so what I've understood, I've engaged with Professor Lily on this a lot, and I've understood that you first learn the sounds like B. B would be the basic unit. So for us, the basic unit is 1. And then you'd start to get words like bat, mat, cat, fat, which then the at is the constant, and you're changing the B. So you learn to sound out bat, cat, mat. And later you get a bigger word that you don't recognize, and you would break it up like into B, at, man. That's how a kid would learn to read it. If they couldn't see it, they would break it up. And it's the same idea with composition. I'm not suggesting maths and literacy can be learned the same, but it's a similar idea of learning parts in order that when you see one that you can't count, you can't quantify, let me say rather, immediately, you don't start to count 1, 2, 3. It's like a child reading B, t, n. They won't hear it's Batman. They need to be able to decode, what we call decoding, and break up into parts. And that's what we want them to do in maths. We don't want them to see 8, not recognize it, and start counting 1, 2, 3, 4, 5, 6, 7, 8. We want them to break it up into what they do recognize. And that looks something like this in the maths. They might see this card, and you might not be able to see that it's 8 immediately, because most of us can only sabotage, like recognize a count with our eyes, up to 6. So none of us should actually be able to immediately see it's 8. But we shouldn't now have to start counting 1, 2, 3, 4, 5, 6, 7, 8. We should be able to see there's 2, there's 3, there's 2, there's 1. That's what we initially do with little kids. We just want them to see 2, 3, 2, 1, that they're at least starting to group with their eyes. And then they start to learn 1 and 2 is called 3. So if I see a 1 and a 2, I call it 3. That is called 3. If I see a 3 and a 2, oh yeah, that's called 5. So now immediately my eyes start looking for 2 and 3 because I know 2 and 3 is 5. 2 and 1 is 3. And then the 5 and the 3 I know is called 8. So obviously I've played out a long process here, but this is something from grade R to grade 1 to grade 2 that should become a very efficient process, that immediately they should actually, yes, see the 5 at the bottom and the 3 and know, oh yes, 5 and 3 is called 8. And they start to recognize the patterns. But the learners really need this automaticity and to start see things in different ways. So again, yeah, we could ask them, what do they see? And yeah, if you're looking in the columns, if you're looking vertically, you'll see 2 and 2 and 1 and 2 and 2 and 1. And that's what the grade R's will probably see for a while. And later on, they'll start saying, that's very long. I can actually see 2 on one card. I can see 2 and 3 and 2 and 3. And so they become more efficient in their groupings. Later, when they know that 2 and 3 is 5, it's become an automatic thing for them. When I see 2 and 3, it's called 5. They'll say, I see 5 and 5. And this is what we're heading for. 5 is our first base. 10 is going to be our next important marker, but 5 is our first important marker. In fact, the ultimate is when they start talking about, I see 2 5s or 2 groups of 5s, or I see 2 5 apple cards, because this is a really hard concept for children. It's easy to describe an object like 3 apples, but now 5 is the object, and you're talking about 2 5s. You're talking about a quantity of a quantity. And of course, that becomes multiplication. So very early on, when we introduce this language, we're already introducing children to the mathematical reason of multiplicative reasoning, which is wonderful. It makes it much easier for them to cross that bridge into the multiplication later on. So ideally, we'd love to talk about this as 2 5s. The name is 10 and the collection is 10, but the description is much richer, and it's all of these things. And so we want kids to see this and know it's called a 5, not 1, 2, 3, 4, 5. And then they should be able to, in grade R, already say, well, now I can see 3 5s. I'm not asking again how many. I'm not that interested that it's 15. I'm not interested at all for a grade R that it's 15. But a grade R should be able to tell me that I see 3 5s, or 3 groups of 5, or 3 dice of 5. But again, explaining the number of dice and the quantity on the dice as 2 separate things. I think 3 of what? 3 dice. Multiplicative reasoning right there, without calling it that, without telling the children about multiplication. We're just showing a very natural mathematical reasoning principle. 5 and 5 and 5, 3 5s. And you can see I haven't even mentioned 15 because we haven't named up to 15 in grade R. Obviously, as we go through the grades, we'll start to talk about 5 plus 5 plus 5. And later on, we'll talk with the grade 2s and 3s about 3 groups of 5. And that is 3 5s. It moves into multiplication. But you can see from grade R, they've almost been led to learn to compute when they get to 3 times 5. With the cards, we also deal with the beginning of place value, because this is a huge part of composition. Of course, is breaking up 10. The kids learn 12 before understanding that it's actually 10 and 2. By the way, I stay away from the names 11, 12, 13, 14 like that. I work with 10 and 1 in grade 1. I work with 10 and 1, 10 and 2, 10 and 3, 10 and 4, so that they really see the break. They call it by its breakdown. They call it by its composition. And later, when they're very comfortable working with 10 and 1, 10 and 2, 10 and 3, I tell them, 10 and 1's got a short name, like a nickname, because it is actually like a nickname. It's called 11. 10 and 2's got a nickname or a short name. It's called 12. It is its name. But it's in the African languages, I know that I speak Sepedi. So when we talk about 12, we talk about Lesume Pedi, 1, 10 and 2, Lesume Taru, 1, 10 and 3. And when we talk about 21, we talk about masume periti. So it's 2 10s and 1. It's such a beautiful direct translation for me that the English doesn't have and Afrikaans doesn't have, because we don't have transparent languages. The African languages are much more transparent. And so it's a wonderful way, if you are a mother tongue teacher of Zulu, isiXhosa, or Tsonga, the African languages, I would harness that completely. I would fully encourage it. And I hear a lot of my teachers tell me that the learners get confused. They say lesume pedi when they meet 20. They should be saying masume pedi for 20. And then I say to them, we'll ask them, lesume is 110 and the T is 1. So 110 and 1 is 10 and 1. Masume is more than 110. You go into your literacy language, it's a plural. And so more than 110 is the 2 tens. And I also really encourage I don't know if there are any Sepedi speakers out there, but in English and Afrikaans, we ask them, how many tens do you see? I see 110 and I see 1 unit. So with the Sepedi, we will ask, Lebona eng, what do you see? And then we will ask them, Masume amakai, how many tens? For example, and mechu amakai, how many units? So that you really make that distinction between how many tens and how many units. And the reason for that is because we want to move here to talk about one box of apples and one single apple, because 11 is 1 and 1, but the 2 ones represent something completely different. The 1 from the box is representing 10 apples, and the 1 single is representing 1. So in the final number, in the actual name and the symbol, the 11 looks like that. But the blue one and the red one represent different things. The blue one is representing the number of boxes, or in mathematics, the number of tens. And the red one is representing the 1 single. And this is how we help them to gain that understanding, by talking about boxes of apples and single apples, because a box has got 10 in it. And so they understand that the symbols, the digits are the same, but they represent different things. And we carry on. Grade 2, grade 3, we talk about what do you see? Yeah, maybe I'm stop there for a second and just ask, what do you see? Ridwan, if you can help me on the chat, ask people if anyone wants to say what they see. Besides apples, some sort of descriptive.
2 tens and 3.
2 groups of 10 apples and 3, good. Or 2
Two
boxes
groups
of 10 apples
Yeah, 2 boxes and loose ones. Yeah.
and loose ones, good. Anything else? What is in one box?
The ones that I saw 2 groups of 10, so they reckon that there's 10 in a box.
Correct. But in one box, there are 2 rows of 5. So you could even say that you see 4 rows of 5 apples and 3
Mm.
singles.
Mm.
Or you could say in one box, there are 5 groups of 2. In other words, I'm seeing 10 groups of 2 apples and 3 singles. It's just a whole lot of different ways that one can talk about what you see.
What you
But
see.
essentially, all right, there are 2 boxes of apples and 3 single apples, which is 2 tens and 3, which is obviously 23. But we often talk about 23 too quickly before we've made that distinction that it is 2 tens and 3 units. And they should be not only dealing with 2 tens and 3 units when we're doing expanded notation. You should be interchangeably talking about 23. How many tens? How many units? So with my learners, when we talk about 23, which in Sepedi is Masume Taru, Masume Pedi Taru, then I'll ask them, Masume Amakai, Masume Amabedi, Mechu Emakai, Mechu Emetaru. So we have to make that distinction all the time so that they keep it in mind. Okay, so I want to stop at this point and just ask, are there any questions so far before I go on? I'm not sure if anybody has the question. If you want to pop it in the chat, we can answer a few questions. I know sometimes you forget your questions if we get to the end, and if anyone does need to run to the bathroom, you can.
There was a question earlier. I'm just trying to get to it. But I think immediately after the question, you show the cards of the computing. But I just want to honor the person who asked the question. Let me just find it.
What is it? What? Working by the order.
Okay. How do we teach our little ones to think like this? That was the computing, I think. Please, may you provide examples of how we as teachers can scaffold computing? In my experience, at the end of grade 2, learners start to show abstract thinking. Do you perhaps have examples of how computing can be scaffolded from grade 1 to grade 2?
So I'm not sure if I've answered that question. If I haven't, the person is welcome to just indicate But I want to start showing now, I'm going to show now how we move from the visual into the symbolic as well. But for me, the cards, the visual is the most important scaffolding, because in their mind, they need to see 3 as 2 and 1. That needs to be a core thing from the beginning. And I think it should be before the end of grade 2 that this kind of abstract, I don't actually think it's abstract thinking, to be honest. I think it's mathematical reasoning, and we can teach it from very early on. And I really hope that this is giving you at least encouragement that we can do that. We're still unfolding material. I will actually talk to material. We have a material available at the end that I'm happy to send out if anybody wants to try it. It's for free. The YouTube channel is for free. So we also got some kiddies videos on there. We're just trying to provide means, and we happy for anybody to give feedback. And if there are specific requests that we can, we really want to support teachers in this so that we can
Yeah.
try it. So I hope, I
That's
don't know
one
if they've
thing.
indicated.
So sorry, just wanted to jump in there. Thank you. It was Antoinette, I think, who asked the question, and she responded by saying, yes, you explained it. He has a bit understanding. And then I think you just answered this question. Somebody asked, where can we get the cards and what is the cost? So that one also popped while you were responding there. So they will be
Okay.
able to get the card somehow?
Yes, the shop is going online on the 1st of September, and if you order them before then, they are 40 Rand a pack. The pack, you don't need a pack for every child. If you want a pack for every child, that's fine. Obviously, schools that are ordering bulk, we can look at some sort of discount. But they're going online for 50 Rand. But for the schools, we do have special prices, but just contact me directly for the bulk orders. I just want to say what we do for schools. We found that to just give a pack of cards to one child and they open it and there's 50 cards in there. It's 10 apple cards, 10 zebra cards, 10 dot cards. They get a bit overwhelmed. They won't as well. We're packaging them in little plastic packets. So we put the 10 apples in a packet, the 10 zebras in a packet, the 10 sticks in a packet like that, so that on any given day, this is just a practical way, the teacher might decide today I'm only working with apples, because we don't really want, unless you're looking at 3 sticks, 3 apples, 3 dice, we don't really want them to mix up, because 2 sticks plus 2 apples is not four somethings. It's 2 apples and 2 apples, or 3 sticks and 4 sticks. We want to keep them the same. So today you could just hand out apple cards to everybody, for example. And the next day you could hand out stick cards to everybody. And the next day dot cards. So the kids get, in a week, they could get 5 different experiences of patterning and spatial orientation with the cards, but you haven't had the chaos of trying to collect all the objects every day. So you have your apple box, all apple cards, you have your stick box, and so we work it like that. So that's how we are dispatching to the schools, which means technically if you wanted to only buy apples because funding was a problem, we have cheaper prices for only buying the apples, for example, because we really want to try and make it affordable for everybody to have them. They are the same quality as a normal pack of cards, by the way, so they do last. Some people have photocopied them, and the problem is it doesn't last, and we've done so much research into the actual patterning and shaping. So yeah, you're welcome to contact me for further, but hopefully, and on the Young Game Changers website, there's also a thing where you can put in a pre-launch, just send us your email and we'll also give them to you at the reduced price for now.
And then there was a Mohadi, I hope I've got his name correct. He said that he's not at the school, but he is absolutely delighted, or he or she, I didn't quite get it, at the aftercare where they assist learners with homework. And so these cards will be very, very useful for him or her to employ at the after school. So I think that is a great
Yeah,
initiative.
that's a great idea. And I can just add as well, we're busy printing, we're busy designing activities where you can just take a printer sheet and then you can, it also helps the children to put the cards out to get a total. And so there's a whole lot of ways of working with them. And I can't go into all of that today, but we filmed a few weeks ago, we filmed a workshop. I did it a lot in Sepedi, but we can use the visuals and I'll do a voiceover in English where we show it right from the beginning. You just play with the little ones, copy me, put a 3 of apples, they copy. You don't tell them it's 3 apples. They find it. And we took it through all the games. I think we had 50 something games in the end that one could play with the kids. So it's not just about using them for composites. We want them to play. We want them to have fun with the cards. So after school would be a great place for that as well. In school as well, it's a great place for playing, but after
Mhm.
school as well. Yeah,
Mm. Yeah, I think it's important that we eliminate this fear of mathematics, you know.
absolutely.
The children needs to have fun, and once they're having fun, learning is going to increase at a rapid pace or a better pace. But sometimes this fear and anxiety, and when it gets to high school, they just opt out for this maths lit, you know. And I think it is at the begin at the foundation phase stages where unfortunately this fear of mathematics is built up in our children. And I love what you're doing. I think these cards is a great, what we call game changer, pun on the word game.
Thanks, Ridwan. Yeah, I'm so excited because I think counting is, for me, counting is not a mathematical skill at all. It's a life skill. Most people can count, but that doesn't mean they can do maths. And I think by counting and counting and counting, we're not enabling the kids to gather the reasoning skills. And then you're right, they get very nervous about the maths later on because suddenly we require higher thinking from them, which hasn't been developed. So, yeah. Good. So this is what we would love to see from grade R kids in our system. If they've gone through using the cards and or using this kind of learning about composition, ideally I should be able to ask a grade R, even a child that hasn't learned the word 10. I should be able to ask them, what do you see? And they don't go, oh, 1, 2, 3. In fact, I have so much footage of grade 5s. I might get time to show you later on, counting each of these with their fingers and then counting again because they lose track of the ones they've already counted. And that's really not what we want. And I haven't specifically used the word sabotaging a lot because sabotaging is often up to 6, and then after that, I'm not sure what happens. I've used composition because we want kids to recognize with their eyes patterns and groupings because that's all part of the math. It's not just about the quantity. It's about seeing the pattern. So I hope you can see with the zebras, it's 2, 3, 2, 3 because they're the hardest to see on the cards. And once you've seen the 2, 3, and you know 2 and 3 is 5, you immediately see this is a 10 card because it's got 5 and 5. So when the kids get used to this, they start to see the patterns very naturally, which makes them look for patterns very naturally, which is a wonderful part of maths as well. So we want them to see 3 from the top, 3 and 2 and 3 and 2. Later, they'll talk about it as 5 and 5 and 2 groups of 5. Again, all of this, as I've said already, laying the foundations for multiplicative reasoning as well. And then, of course, we know the name is 10. So in grade R or grade 1, they already actually know the quantity and they can describe the quantity. And we just tell them the name is 10. And so often I find in schools, kids are learning the symbol first from 3 years old, which is terrible. I'm not going to talk about that too much today. But I really think the first thing children should encounter is the visual picture of quantities. And that's also why we have the cards. They shouldn't encounter the symbol first. But I find even in grade R in our schools, they are forced to learn the symbol, the quantity name, and how much it is all at the same time. And I think that can become very confusing. So we try to teach the quantity up to 5 in terms of the description. And then from grade R and grade 1, we start to talk about the names higher up as well. Then in grade R, you already should have a child. And again, I'm not using symbols yet, so I'm not talking formal mathematics. But a grade R who's used the card should be able to tell you that they see, oh, I see 2 and 3, but that's called 5. And then I see 2 and 1, but that's called 3. So what I actually see is 3 and 5. But wait, I know, or 5 and 3. I know that 5 and 3 is called 8. A grade R will now know it's called 8, and they can replace it with the 8 card because that is what the 8 card. Another thing here is happening is kids are using spatial composition. They're changing the structure of the cards that are next to each other, put them under each other, and then they can go look for the one card that replaces those 2 cards, which is the 8. So that's how it starts off in grade R. In grade 1, when we start getting to the formal symbols, this becomes a plus. We have formal symbols in mathematics, which we teach them, and we have a symbol for that in maths, which is plus. 5, we have a symbol which is 5, and we have a symbol which is an equal sign. So the only new thing in grade 1 for them, they know the name, They know the visual picture, what it looks like. The only new thing then is the symbol. Whereas at the moment, the symbol, the name, the quantity are all new to them at the same time often. And then that is what translates into the computing. So now they've learned that 8, they've seen an 8, and they know that an 8 is 5 and 3. So they work much more easily with 8 as being 5 and 3, and 7 can be 5 and 2. And now it becomes very natural for them to put the two 5s together. And I know 5 and 5, I showed you the slide earlier on, is called 10. So 5 and 5 is called 10. Let me see what's left. 3 and 2. Oh, yes, 3 and 2 is called 5. So I'm left with 10 and 5. And I know that 10 and 5 together is called 15. And so that is computing, not counting on, not counting all, computing from composition. Another way they might do it is they might be comfortable to only break up the 7 into 5 and 2. Those 2 from the 7 shift to make up from the 8 a 10. Again, we call it, I don't know, the method is called composing to the nearest 10 or going to the nearest 10 or something. But that again is not taught as a method. It becomes a reasoning that they understand, and they are actually able to manipulate and move the numbers around. And so reasoning is required in both of these, and so is computing. Again, with the zebras as well, 5 and 3 and 5 and 2, it's the same thing, but you'll see the different patterns now. So they have to look for different groupings. 2 and 3 is called 5, 2 and 3 is called 5, 5 and 5 together I know is called 10, and the 3 and 2 that is left gives me the 5, which together is 15. So this becomes a very natural thing for children then to start computing, because they've learned the numbers as composites. They're used to building them, breaking them up. They use breaking them down, building them up, and they are the ones who get to manipulate and gain confidence in that. Again, they can take the 2 from the 7 over, and they've got 10 and 5. But you can see they get, the idea is they get a lot of practice with all the different sets of cards so that they get the feeling of manipulating different objects. And so what does that look like in grade 1? This is what we would like to see in grade 1. I've shown you earlier as well, the 8 becomes 5 and 3, the 7 becomes 5 and 2. And by the way, this can be done with flat cards. So we sell the quanti cards, we also sell the flat cards, because we do have to move from visual to symbolic. And so the quanti cards are a visual resource. They're also still semi-abstract because they're not actually like bottle tops you're counting, but the symbolic, the flat cards are more of a formal manipulative, because they now represent the visual. They don't have the pictures on anymore. So we move from the quanti cards to the flat cards, and they actually physically pack out 5 and 3 because they know 8 is 5 and 3. Put the 5s together, makes a 10 card, and the 3 and the 2 makes a 5 card. And then the wonderful thing about the flat cards is that they can be combined, and you see the 10 and the 5. It's not just a 1 and a 5, it's a 10 and a 5 that makes 15. So let's talk about this going into grade 2 and 3 and continuing by computing. Let's look at 18 plus 17, which is a grade 2 problem. We would ask, for example, the kids to, and I've done this with teachers as well, first calculate this using your quanti card. So you first get a visual picture of moving the objects around. Then you show the procedure using the symbolic, which is your flat cards, but it's still a manipulative. And only then do you write down what you've done. So the difference here in how we're doing, how I'm seeing things in many classrooms is we show the kids an example. We put 18 plus 17 on the board. We break up 18 for them. We say it's 10 and 8, 10 and 7. We show them the method and they copy our method. What I'm suggesting is they do the manipulation visually, physically, and then write down what they have done so that it becomes their procedure that they have computed and not our method that they have reproduced without understanding often. And that looks something like this. These are our stick cards, and the grade 2 and 3 quanti play cards. The sticks are done like tallies for a particular reason, to get children to understand tallies as well. But you can see there's a 10 card and an 8 card and a 10 card and a 7 card. And the natural thing now would be, what do you see? I see 10 and I see 10, which is 20. And I could take the 2 5s from the 2 cards and make 30. And now I can immediately see the answer. I'm not counting. I can see the answer by computing, by grouping and making the natural groups. And then I do it with the flashcards. So I pack them out. I split up the 18 into 10 and 8 and the 17. And watch the beginning when kids work with flashcards, they mustn't work with 18 as a 1 and a 8. It must be a 10 and a 8, and the 8 goes on top. Again, you put the 10s together. And now the 8 and the 7, the wonderful thing with the flashcards is you have to 8 and 7, you can't put a 1 and a 5. You have to put a 10 and a 5 to make the 15. And this is fantastic for the foundation phase, because now they're really understanding that 15 is 10 and 5. It's not 1 and 5. And the 20 and the 10 again get grouped together, which is 30 and 5. And then I recompose, and that is 35. So I've gone from the visual to the symbolic, and now the child writes it down. They write 10 plus 8 plus 10 plus 7. And so, yes, some people tell me this is the horizontal method, but the child is purely writing down what they did with the flashcards. So they take ownership of this process. The 15 becomes 10 and 5, and the answer is, of course, 35. They could even do the flashcards like this. There's no problem doing the flashcards, laying them out vertically if you want. Again, the 8 and the 7 is 15, but now I can actually see that the 10 goes up into the tens column, and I've got 3 tens, 10, 10, 10, or 3 times 10, or 10 plus 10 plus 10, which is 30. And now I can clearly see that it's 35. There's not that error of working with digits. The children are really working with the values as decomposed values. And the dot cards, similar thing. You can see the 10 card, you can see the 8 card, and the same thing there. 10 and 10 is 20. I can take 2 from the 7, which makes 30, and I'm left with 5. And so it's a lovely visual reorganization and manipulation. So I don't know how your learners will do this. 7 plus 30 and 100 plus 7. I don't know if some might count on, some might draw sticks, some might just know that it's 37. But this is what we're seeing. We assessed about 15,000 learners some years ago before COVID. And unfortunately, we're seeing quite a lot of this. We're seeing a lot of sticks being drawn. And counting all or counting on becomes very inaccurate and laborious at this point. If learners don't have the mathematical understanding of decomposition, and they've only been relying on counting or drawing sticks, this is unfortunately what's going to happen. They need to understand that the 100 is 107 units, and then to be able to write that as 107. And so this is more of what we are seeing. You can see on the left-hand side, I think this is happening because methods are being taught without understanding. So the learners are being shown a method, in this particular case, a very a horizontal method, break up the first number into 2, break up the second number into 2, and then try to group them somehow. But you can see there's a complete lack of understanding of the numbers. And this is worrying me a lot, that a sum like this has become an impetus for a child to follow a method. What method did the teacher use? And let me try to follow it. So they're engaging with the method instead of engaging with the actual values that they're confronted with. And composition should address this, because they should be very comfortable. 7 and 30 is 37. I've got 3 tens, and I've got 7 units. So it's 3 tens and 7 units is called 37. The same with the 100 plus the 7. Look at the numbers that they're coming up with. The numbers don't even make sense. They're just a whole lot of digits, and this is what's concerning. I can show you probably thousands of examples. You'll see the one on the number E on the right-hand side. The child actually tried to split the 100 into 10 and 0, because not value-wise, but digit-wise. You'll see how often the children are interacting here with digits rather than with the actual number. And I think this is coming from the symbolic preceding the understanding of the values that they're working with, and hence the quantities, and hence the composition we are trying to teach. And again, a lot of engagement with the symbols, 7 and 30, 3 and 7, 0 and 3. And a lot of this comes from the teacher saying rules like add the 2 first digits and then put a 0 on the end. So the child tries to add 3 and 7. and get 10 and then put a 0 on the end, and that causes a whole lot of problems as well. The same with the 100. Because children have become so conditioned to count, they can only manage symbols below 10, and so they just break everything up into a symbol below 10. And again, there's total lack of understanding and total lack of computing. Even though this looks like it should be computing, it's not happening. So here's a question. Does this learner have a sense of number? I'm going to wait this out in the chat for somebody to be brave enough to commit. If you were a teacher assessing this grade 3 learner, would you say they have a sense of number? Would you be happy?
Maybe a person with an answer can just unmute themselves and we hear what they say.
Great. We've got time. I'm nearly at the end.
Okay. Bridget says yes.
Fair enough.
There's a few more which says yes, the child or learner has their own reasoning and is able to get to the answer.
Great. I agree. The learner has done it correctly. They've decomposed the 35 into 30 and 5, 20 and 8. They've regrouped. They've even added the 50 and 13 to get 63. I'm going to show you exactly the same learner doing another sum. And now tell me if you still agree. Anybody's welcome to comment or unmute yourself.
Somebody says, oh dear.
Yes.
Yeah, some knows because they can see now, and then somebody says, oh dear.
It is an oh dear, and this is the deception that we are seeing. This child, I don't think, has mastered the use of symbols, the Arabic symbols that we use, our number system. I think this child has mastered a format. They've mastered the method. And when the method has been deviated from, for example, there are no longer two numbers, it's 98 and 5. Now they're trying to follow the method again, breaking up the 98, which the child can do. I'm not sure if they understand what 90 and 8 is, but they can break up 98. And then they've got 50 and 5 because they didn't know what to do with the 5. So they're trying to follow that formula, but there's no other number. So they just made up one, 55, and then followed, of course, the same procedure, and then again got into trouble with the 90 and 50 and decided that it should be 95. I'm not actually sure what happened there. And I think 8 plus 5 they perhaps thought was 12 instead of 13. I'm not sure. But you can see how quickly it can go horribly wrong with a learner that you think actually knows what is going on. And again, it goes back to, are we teaching learners to count? Are we teaching them to follow a method? Or are we teaching them to compute? So here's another one. I'm going to show you the same learner again. Again, we probably all in agreement, correct? Learner looks like they're doing fine. Again, exactly the same learner. It's a different learner from the last screen, by the way, but these three that I'm going to show you are all the same learner. And again, you can see when it's in the nice formula and method that the teacher followed, probably. And again, I would contest the use of brackets in foundation phase. I don't like it because I don't think it's fully understood. But that's a personal choice. Again, subtraction does bring its own problems. But if a child understood the value of numbers and the value of quantities, they literally should be able to count backwards on B. I mean, this is a point where I would count. Even me, I won't go do 103 minus 5. I'll probably go 102, 101 with my fingers, unashamedly. 102, 101, 100, 90, 99, 98, literally, because it'll probably be my quickest. Unless you're happy to say 103, wait, 5 is 3 and 2. If I take 3 of those, I'm at 100. If I take another 2, I'm at 98. That is reasoning. So again, I'm not saying counting where it's the quickest, by all means use it, but you still need to be able to compute in other places. But when counting's quicker, the thing is to have the understanding of the numbers to be able to play around with them. And that's what makes computing, when you have that understanding. Again, the same learner, getting an answer of 98 plus 5 as 45. So correctly breaking up the 90 and the 8 and the 5, and then realizing, oh dear, the 5 doesn't have a partner or whatever they needed. And so I think the 8 got given to the 5, and another 5 got given to the 90. I'm not sure what happened there, but you can see a total lack of appreciation of the actual quantity or the actual composition of the numbers. And these are the results which we're seeing with many, many learners. And perhaps today you're looking and saying, but wait a minute, I'm seeing this with many of my own learners. I'm not sure. And this is the result of trying to use written methods without mathematical reasoning. So before there's been an understanding of the computing, there's been an opportunity to see visual manipulation. There's been an opportunity to work with the flot cards in symbolic manipulation, and then only writing. This is the method preceding all of that. I want to show you a video of a grade 5 learner. This is a study we did, I think 2 years ago, or yeah, last year, on an intervention with grade 5s. And I want to show you what I'll show you, and then I'll deliver comments. Anybody want to comment on that? I never watched this video without feeling increased levels of discomfort and sadness, actually. So I don't know if anybody wants to unmute themselves and comment. You're welcome to just stop me. But you notice that the learner could identify up until 4. And after that, what saddens me the most is that the learner didn't even grab the card that had less apples on it. They just started randomly grabbing cards and counting. And this is the danger of counting, that we just can't. We'll find it by counting. And this is our apple test. We call it the apple test. We get learners to order the cards. You mix up the 1 to 10 apple cards, and you get the learners to order it from smallest to biggest. And it's actually been a really good indicator. We're busy writing this up because we found this to be a really good indicator of the performance of the learner actually in their mathematics. So this learner is not performing badly, but she's not able to go beyond a certain point, really struggling with multiplication and division because it's involving a lot bigger numbers. And I don't know if you know the research, but there's a whole lot of research on spontaneous numerosity, like being able to recognize quantities. And babies of 6 months can already tell the difference between a lot and less. Even elephants, chickens, if they repeatedly gave elephants a lot of stuff to choose from or a small amount, and they went for the big amount of food. And they are able to distinguish. And we are born with that, actually. And then we have a grade 5 who's gone through the school system and is no longer even practicing that. She's not even sorting the bigger cards on one side and starting to then count them. She's just grabbing cards and counting. And I think this comes from a habit of us as teachers often saying, let's count. Even when children know something is 4, we say, let's check, let's count. And so counting becomes this ingrained thing. And so our hope is really that kids would be able to order these cards by recognizing with their eyes through a decomposition who have gone through the system. And we did actually take these grade 5s through a course, and there definitely was some improvement. We have the after Apple test as well. But it really saddens me that, yeah, and I'll be honest with you, I've trained a number of teachers all over the country who are also counting with their fingers, because it's not anybody's fault. It's just that's what we've been trained to do. We've been trained to count in the foundation phase, rather than to compute. So these are some of the activities we have available, and they are free PDFs. I'll put them on they'll be going on the website in the next while, but if anybody wants them so long, you're welcome. They're much bigger than this. This is just an example of what they look like. They don't have to go with the cards. You can do them independently of the cards. But the whole point is this approach of teaching the kids to differentiate between what do you see, which is a description of the composition, and what is it called, which is the name. So what you see here, and there's more than one way to describe it, is 2 apples and 3 apples, or 4 apples and 1 apple. We're trying to move away from 1, 1, 1, 1, 1, because we want them to see the groupings. And what is it called? It's called 5 apples. So this is a way of training even grade 2s and 3s to start seeing the groupings rather than just seeing the name or counting 5 apples. We're not asking how many. There's the 4 and the 1 and the 2 and the 3. And the same, yeah, we leave the 2 lines, 2 different ways of saying what you see. You might see 2 and 3 and 1 because it's a natural grouping. You might also see 3 and 3. Some children may say they see 2 3s, some may see 2 and 1 and 3, all correct, but it's called, yeah, there's just some other option. It's called 6. So we're getting the kids as well to understand the difference between what I see and what it's called. A number is not just a count. A number can also be made up of descriptions of smaller numbers. And then getting into the grade 2 and 3 work, what do you see? We've already spoken about one like this. I see 2 boxes of 10 and 1, or maybe 10 and 1 and 10, or 2 10s and 1, or 11 and 10, many different ways to describe it. But it's called 21, or 2 10s and 1 if you're dealing with grade 1s. So me personally with the grade 1s, like I said, I work 10 and 1, 10 and 2, right up to 10 and 10, which we then call 2 10s. And later we only start to call it 20. I want them to work with it before I give them the more complicated name. The zebras are in little paddocks. So now we're talking about groups of 5. So this brings in the element of maybe seeing 10 and 10 and 2, or maybe seeing 10 and 12, or even seeing 4 groups of 5. All sorts of different, it's not looking for a correct answer. We're just looking for a description that does address the quantity of what we're seeing. And again, encourage the children, we are talking about quantity. And it's called, yeah, there's the 5 and 5 and 5 and 5 and 2, or 4 groups of 5 and 2, 5 groups of, oh, I want to ask you about this one, 5 groups of 4. I see this 5 groups of 4 coming up sometimes, and I know that 4 groups of 5 is 20, and 5 groups of 4 is 20, but this is not 5 groups of 4. So 5 groups of 4 would not be a correct representation of what you see here, because they are not in groups of 4. They are in groups of 5. So there are 4 groups of 5 and not 5 groups of 4. Because we also want the children to get correct descriptions of the representations they see. But either way, it's called 22. I want to end off with just talking a little bit about neural pathways. And counting versus composition. I don't know if you know, in our brains, when you encounter something new, you form a neural pathway. If you keep doing that same thing again and again the same way, you will strengthen that one neural pathway. So it's a bit like if I follow the same path to school every day, that dirt path will get worn out. That's kind of like one neural pathway in my brain forming. If there was then a flood and I couldn't cross that path, I probably couldn't go to school because that's the only path I know. And this is what happens with counting, unfortunately. It's the only thing I know. It's the only way I know how to get to 8 is 1, 2, 3, 4, 5, 7, 8, and then 7 and 7, and then I count all, and I've got that one very strong neural pathway. But when I can't use it, I'm stuck. And we want children to go from counting to computing, but the only pathway that we've installed from a very young age when they've got brains like sponges is the counting and the counting and the counting pathway. So the idea is that you would rather like to have different routes that you can go to school, so that if one was blocked, you would have another option to go, and that would create different pathways. When Sorry, something's not moving. Oh, it's the little pathway. So when a person learns something new, they form a connection between two previously unconnected neurons. And if that connection is weak, the new thing will be lost. But if that connection is strengthened, the more and more connections get very strong. So all of these are ways that we would like children to meet five. We would like them to know it's five. 5 rand, 5 apples, 2 and 3 apples, 2 red blocks and 3 orange blocks, 3 zebra and 2 zebra, the word five, 2 and 3, 2 and 2 and 1, 2 and 3, a dice of five. All of these different experiences of the quantity of five before they even meet the symbol, and they can meet the symbol later, and before they even meet the count of 1, 2, 3, 4, 5. All of these different experience of fives develop this much stronger network of 5 neurons in their head than that pathway of 1, 2, 3, 4, 5, because then I always reach 5 by the count of 5. And that's the whole idea with all of the cards and the different arrangements and the different spatial thing. It's also on the cards about seeing there's a bigger blank space with 5 than there is with 8, for example. So a whole lot of things that are what we call subliminal that the kid is learning without learning. They're just learning through playing. So it's the connection that we want to talk about. So learning numbers as counts, it purely teaches them that 4 comes after 5, and all of this is necessary. It's not wrong. 4 comes, after 3, or it becomes before 5, and that's what it looks like. But the richness, and by the way, counting also teaches cardinality and ordinality, one-to-one correspondence, basic addition, and then, of course, mastering formats, as we've seen. And none of this is wrong. But it's so small, and it's such a small package compared to learning numbers as composites. You can partition and combine. 3 and 2 is 5. 5 and 5 is 10. 30 and 7 is 37. You can also talk about the number of numbers. I can talk about 3 groups of 2. Later I'll learn that it's called 6 or equals 6, but it's 3 groups of 2, 4 groups of 9. From a very young age, I'm dealing with multiplicative reasoning. It deals with breaking up, building up and breaking down, which is a very natural part to computing later. It helps them to understand place value, and it helps them to understand equality. All very important mathematical reasoning principles, as is the unitary principle as well. And then it helps computation without a dependency on format. Those kids that we saw going wrong, they went wrong because they were dependent on the format and not relying on their own sense of number, because it probably was not strongly in place. And lastly, it enables them to be mathematical reasoners, not just counters, and to do problem solving. So my thinking is, if you have all of this that you can start developing from 3 years old, why not? Again, it's not that counting is bad. I had this group the other day. After a workshop, we have like a group with the workshops that I do, and somebody wrote in Sepedi, counting must fall, like fees must fall. It was like that sort of movement. But I'm not, please, I'm not the initiator of counting must fall. I don't think it's a mathematical skill. I don't think it's a mathematical reasoning principle, but I don't think it must fall. I use it myself on an Excel spreadsheet. Trust me, when I have to count, I count the number of columns or rows. I do not try to visually. But in mathematics, it's not teaching the principles. And it's not that it's bad, but it's what the learners don't learn by only counting. So their brains can be absorbing so much more, and we only count data of the learners. So it would be wonderful if we could make a greater focus on this. And I'm done. Any questions? With those 3 minutes you told me to give, Nomhlanhla.
Yeah, there was one question so far that popped earlier on, and how do you teach subtraction with the cards, or is it mostly used for addition?
Absolutely can be used for subtraction, especially in conjunction with the float cards, but I would need a whole workshop for that. I did a whole workshop on that in series about 2 months ago. And we're going to be getting all of those will be broken up into videos. Ubuntu are actually sponsoring the making of the videos. So that presentation, I don't mean videos of me talking, small 5-minute slots that teachers can watch, or even kids can watch, that addresses how to use the float cards and the cards for doing subtraction. Because subtraction is not just takeaway. I'll just give you a short, quick idea. I don't have cards with me. Let's say you've got a 5 card and a 3 card. We often only think of subtraction as takeaway, but that's only one thing. You can take away 3, and that you can't do on the cards. You can't literally take away 3. There you need objects. But you can have a 5 card and a 3 card and ask the learner, are they the same? Are they equal, first of all? No. Which one is more? Which one is less? And I do this with my teachers in one of the games. This one is more, this one is less. How many more or how many less? So I would take 2 there, then they would be equal. So this one is 2 more, this one is 2 less. What would I do to this card or this hand to make them equal? I would have to add 2 to this one, or I would have to take away 2 from this one. And so that's the idea. We use it a lot because takeaway, subtraction is actually difference, which I've just done. It's take away, which we take away actual things. And the other one is that it's how many am I short? I want to buy bread. The bread costs 8 Rand. I've got 5 Rand. How much am I short? And it's actually much more important that learners understand those contexts of subtraction before we actually do the actual calculations. But we often do it the other way in South Africa. We teach them the calculation of subtraction before they've understood what we're doing, and we show them the methods, and then we give them word problems using subtraction, and we expect them to apply the context without having actually understood what they're doing. So we prefer to put the context first using the cards or using other manipulatives, and then so you literally start with the word problems, and then you move to them actually manipulating and computing, and then the writing down. So for us, the writing down method is the last thing, whereas often it's the first thing at the moment I see in classrooms. But yeah, that's a very short answer for something that needs a whole workshop. We can always do a workshop on that.
Of course, yeah. Yeah, I think you've created quite an interest. There was another question here that I just wanted to get back to again. Let me just see how to get there now. What about learners who struggle to learn visually and would need more practical hands-on activities? Are the cards quite limited with regard to those specific kind of learners, or would you then add other manipulatives?
I would add other manipulatives anyway. The cards are for me just a starting point, and we've actually I don't want to do like a whole product advert. So let me just say there are a number of manipulatives we have created. We've actually created a whole quantity range, and you'll see on the website when it gets released. But we have numbered tracks for learners to physically work on, because my own understanding is the body is the easiest way to learn first. So I will start with the hands. So the cards are just an easy tool to have in the classroom, but I'm in no way suggesting they are the only tool. I actually, in my approach, and you'll see it, I think, on the videos as well, I completely support as many sensory input opportunities as possible. I want kids using all the senses, because the neural pathways will grow from the different senses. So the cards are the visual tool, and they are a starting point, even for kids in grade 2 and 3 who have not met numbers as composites. But for example, we do auditory. Like I often ask the teachers, what sound does a cow make? Obviously, it goes moo. Then I ask them, what sound does a 3 make? And then they all go 3. That's not the sound that a 3 makes, by the way. A 3 goes, or ba ba ba, or whatever, but that you actually hear the quantity of 3. So 3 does make a sound. It's hearing the quantity of 3. And then, of course, you want to hold 3 things in your hand. There is that part. We can't ignore that, and I'm not suggesting we do. And then there's also the 3 steps you take. I find on a number line, or when kids are playing games on a board game, they throw a 3 and they're sitting on 2, and they first jump on 2, and then on 3, and then on 4. They don't move 3. So we've created, and I'm not advertising, I'm just really love this thing. It's a track that kids can walk on. It's called a quanti track. It doesn't have numbers on it. It has 1 dot, 2 dots, 3 dots. So it has a visual dot, but you can physically move the 3, because we want them to get that feeling. If you want, give them 3 chocolates to eat as well, so that they
Three Smarties, yeah.
kids can. We've got you know those pop-it things? It's like a 10 frame. So for the kids who battle visually, you can actually pop 3 of them if you want. And then you can see on a 10 frame that 3 of them are popped. And so we want kids, especially kids who have got autism and that, the visual, they need to feel. We have things you can feel. So I'm not suggesting it's the only resource. It's just an easily accessible resource that can be handed out in a class of 40 kids, but by no means the only one. thing of 30 bottle tops and we're counting 1, 2, 3, 4 to 30. Rather put it into groups of 5, or, find ways to work with the bottle tops that's not counting in ones. That's really using composition and encouraging it. Yeah.
Mm. Yeah, so Doc, just a few ones. Is Antoinette says this was so valuable. Thank you so much, Dr. Hannah. It was
Thank you, Antoinette.
insightful. And then Yvonne also said, thank you so much. I really appreciate. This is so helpful. And then
Pleasure.
Lisa said, oh, Lisa, we read that one. Um, oh, yes. And Yvonne further said, thank you for this workshop. Would love a workshop on subtracting. And then thank you so much for sharing. Informative session. Really appreciate. That's from Florence. Emma says thank you. Lisa says thank you. Sandra, very, very interesting. Uh, Johannes says thank you so much. Always good to learn something that come from the nin. I can't see so well. The nin. And
Okay.
somebody's Roxanne says eye opening. Thank you. Mm.
It's a
And
pleasure.
then
Thank you so much for
Gabu
being
says,
here.
Gabu says, this has been the best session. Please do it again. So well done to you. I think it was crystal clear, beautifully
Sorry.
paced, and I think people could get an insight into how they can perhaps read, become reawakened in the sense of computing and not counting. And I think if our children can master those computing skills, then I think maths will have a much better place. So thank you for all the hard work that you put in. I know this is an hour session, but there's been a lot of thinking in the session in preparing for this and to get the work out there. So we celebrate you and we salute you for giving South Africa's clever kids a better chance. So thank you so much.